Hey guys, it's Mr. Ross. I was, oops, sorry. We're going to go through a couple of bits and notes on plate tectonics and the different plate boundaries. Yesterday, you guys should have learned a couple different things. We're just going to review those real fast. We learned that the work from Alfred Wegener and Henry Hess kind of contributed to this idea that the entire planet is broken up into these different plates, and these plates move relative to one another. If you guys look right here, this is one of the plates. Over here is going to be the oceanic plate, which is really, really dense. Continental plate, which is less dense, and they ride along the asthenosphere. Remember, with the asthenosphere, there's these convection currents that are going on, and they very slowly will drag all this stuff along. So we have plate movement all along the entire Earth. Part of the evidence that Alfred Wegener used to determine that plates move was he noticed that if you look right here, South America, which is right there, and Africa especially look like they kind of fit together. We came up with this idea of Pangea, which was all of the continents were once connected, and as we see throughout time, they kind of drifted apart to their current positions. Now again, this is another picture of kind of the suture that was made in between the different continents, and then as they drifted apart to their current positions. Some other evidence we have for continental drift, and then this is just review again. We have fossils of the exact same organisms on separate continents. The only way that could happen for some of these was if at one point the continents were connected. So you can see these bands for this Cynognathus. This thing was in South America and Africa, so it couldn't swim across the Atlantic Ocean to get to one or the other continents, so it had to have been on all these different continents. We also have things like this plant, Glossopteris, was in Australia and Antarctica and India and pretty much all over the world. For it to have been in Antarctica would have had to have been in a much warmer location, so that just shows even more that the different plates have moved over the years. We also had evidence that there was this giant suture on the ocean floor, and this was Harry Hess who figured this one out. There's all these rifts throughout the entire ocean on the ocean floor, and this was evidence for seafloor spreading. Again, picture of some of the undersea mountains that are caused by the mid-Atlantic ridge and some of those other seafloor spreading centers. We also had evidence for just these switches in magnetism. Right here, magma comes up, and the rock that forms has the same magnetic orientation as what the Earth had at that time that it was formed. And as you kind of go farther out, you see that we have these alternating patterns which line up with each other, both with their polarities and actually also with age as well. So the age of the ocean floor over here was the same as the ocean floor over here, and you can do that with all the bands basically. So again, in the Pacific, we see the exact same thing. Ocean age, the red areas which are closest to this suture, these are the areas that formed at the same time. As we get farther out, it gets older. All right, so quick check. What causes the movement of the plates? You guys should remember that from yesterday. If you don't, check out this little video here on YouTube. I'm going to try and hyperlink this on the video so you can just click it, but it's a very good visual. It's only about a minute long, so it'll kind of show you the next stuff we're going to talk about as well. So for the rest of the video, here's what I want you guys to be able to do. We are going to talk about different plate boundaries. Those are areas where plates are interacting or they're coming together or spreading apart or whatever they're doing. So I want you to be able to identify the different boundary types. So you might want to take notes on this. Oops, sorry. You need to be able to tell what the different types of crust will do when they're interacting with one another. So more dense crust is going to sink, less dense crust is going to float up. I want you to identify some of the features that are created at these boundaries and explain how those different features are made. So let's get into this. There are three different types of boundaries. The first one is called a divergent boundary. Divergent boundary is where things are coming apart, they're diverging dividing, whatever you want to call it. But new crust is kind of pushing up, and we're going to get to that, and pushing stuff apart. That would be like at the Mid-Atlantic Ridge, like we were looking at. Convergent boundaries are where things converge, they come together, and there are actually 3 types of those, so we'll talk about that. And then transform boundaries are where things are sliding past one another. There's not any new crust created, there's not any crust destroyed, it's just sliding past one another. So divergent, we're creating new crust. Convergent, we are destroying old crust, or sometimes we're just deforming the crust. And then transform boundaries, we're not creating or destroying any crust. So this is a picture that has all 3. If you look right here, this would be a transform, divergent, convergent. Okay, we have a convergent between oceanic crust and oceanic crust over here, a convergent between oceanic crust and continental, and then we also have a spreading center here. This would be the divergent boundary. And it doesn't really show on here where the transform boundary was, but over here is a spreading center again, a divergent boundary that happens on land. So divergent plate boundaries, basically what happens is we have these areas of the asthenosphere that are melting. They are pushing their way up from those convection currents, remember? So these would be the areas where stuff is heated, rising, and it pushes apart the crust at different places. It creates these mountain ranges, but it also in the center creates these things called a rift, these little depressed areas at the top of the mountains. Okay, so let's take a look here. Convection currents rise, like we said, and the force rips the plates apart, pushes the plates upwards, causing mountains, volcanoes, and the convection cells will drag the plates apart. One of the most notable examples of these would be the Mid-Atlantic Ridge. This has been studied for years and years, since the 1960s when Hess discovered it with all of his Navy exploration. One important thing about the Mid-Atlantic Ridge is this actually is able to be seen on dry land when you go up to Iceland. The Mid-Atlantic Ridge runs right through Iceland, and we can observe the volcanoes there. There's actually a lot of volcanoes that happen in that area. One notable example, there was a volcano that erupted in the early 1800s, and it created so much carbon dioxide that it killed thousands of sheep in this little area where it was, and it actually threw up so much ash and dust and everything else that it kind of clouded out the sun for an entire summer, and it was snowing in the summer even in Europe and North America. So picture of some of the volcanoes that we have up in Iceland. This is a picture also of Iceland. If you look here, we're looking south, so down at the top, or sorry, up at the top of the picture. That would be southwards, so you're looking kind of backwards. Over on this side would be North America. This side over here is going to be the Eurasian plate. And then this, it's kind of darkened in here, but you can see there's a very, very clear kind of canal or whatever you want to call it. That's actually where the Mid-Atlantic Ridge runs for this part of the plate. Okay. We have another example of divergent boundaries. Divergent boundaries also happen on land, and the example for that one is the African Rift Valley. Basically what we have here is we have all these volcanoes, and you guys should have seen this on your maps that you were making the other day. We have these random volcanoes that aren't occurring near a plate boundary, kind of in this area. What's happening though is there's a convection cell there that is tearing this part of Africa apart. So eventually, I want you guys to take a guess what's going to happen to this part of Africa over here, what we call the Horn of Africa. So we have all these plates coming up, and they're kind of pushing their way through and doing the exact same thing that we did at the Mid-Atlantic Ridge, except it's happening on land here. So you can see right here again very clearly this big rift valley. Okay, there would be volcanic activity, or there used to be volcanic activity there. Things like magma push their way up. They create all these little fissures. Those fissures and cracks allow magma to seep up, so we get little volcanoes. We also get these areas that kind of slump down because of all those cracks. Things aren't holding them together. They slump down. This is actually how the Atlantic Ocean formed as well, just so you guys know. So the Atlantic Ocean, the Mid-Atlantic Ridge, was originally between Africa, North America, Europe, and South America. And basically this whole process happened. Once everything kind of was torn apart, it was a lower area that filled in with water, and that's actually how we got the Atlantic Ocean. And we'll probably, well, I'll let you guys decide. Based on the map, what do you predict is going to happen to the African plate all along here in the future? This is one of the questions I would like you guys to answer. Okay, so East Africa might be the site of Earth's next major ocean, if you didn't already answer that question. The interaction of the plates in the region provides scientists an opportunity to study what happened in the Atlantic, kind of like I said. If this spreading continues, eventually the African continent will kind of rip in half. There will be two big chunks of it, and the Horn of Africa will be out in the Indian Ocean. So, all right, next we have convergent boundaries. There's several of these. There's three different types: ocean to continent, ocean to ocean, and continent to continent. Those are the different types of plates that are going to be involved. So, the first one here, oceanic to continental. We have the lithosphere and the crust coming at one another. Okay, so that's all that a convergent is. The different things are converging. They're coming at one another. When that happens, oceanic crust, because it is more dense, will dip below continental crust and sink below it. When that happens, a couple interesting things occur. The oceanic crust in the ocean, where it meets the continent, we get this deep valley called a trench, and these are some of the deepest areas in the world. We're going to talk about a couple more of these. You have this on the west coast of the United States, all along California, up along Washington State, and up into Canada and Alaska. So right here, when the oceanic crust dips below the plate, the continental crust, it will go down, and all the pressure and heat will actually melt the rock and cause it to bubble up and create volcanoes. So along these long plate boundaries, we have lots of volcanoes all along here. And we're talking not just like one or two. We're talking about miles and miles and hundreds of miles worth of volcanoes. You look along the western United States, and that's exactly what's happening. So again, remember, I want you guys to know what are the different kind of features that are created by these. So with an oceanic to continental boundary that's convergent, you would have a trench, you would have these volcanoes, get some mountains in here. Okay. Another example, the convergence of the Nazca and South American plates. They have kind of deformed everything, and they've pushed up to create the Andes Mountains. Okay, the Andes Mountains, the Rocky Mountains, all of those different things are created by oceanic to continental convergence zones. All right, here we're going to look at oceanic to oceanic. In this, it's pretty similar to what already happened that we saw before, but we have one oceanic crust that is just for some reason slightly more dense. If you guys look here, it actually bends the upper crust a lot more, and we actually get deeper trenches with these oceanic to oceanic boundaries. Let's go back for just a second. See how there's not that bending in the crust right there, but in here we have this great big bending. So we have very, very deep trenches in the oceanic to oceanic convergence zones. If I was to ask you what kind of convergent boundary creates the deepest trenches, you would be able to say oceanic to oceanic crust. The other thing is we're still going to have this melting of the plate, bubbling up and creation of these volcanoes, and this happens in like a long arc. We get these long chains of volcanoes that happen. If you look up into Alaska, the Aleutian Islands, that's an example of where you would find some of these. Okay. You also have all of these convergence zones all along these places. Some other ones would be, if you go out here, the Philippine plate is kind of being outlined by me right now, and right here the Marianas Trench is the deepest trench in the world. Challenger Deep, which is near Guam, is the deepest point in the entire world. If you were to take the Mount Everest and place it in there, it would only go about a third of the way up there. But again, oceanic crust here, oceanic crust here. We get this long chain of volcanic islands. Okay, this is called an island arc. All right. All right, we're going to break here for just a second and just take a quick look at the Challenger Deep just so you guys can get an idea of what it looks like. I'm going to, oops. All right, so we're looking on the map here. right along here, this very dark area, this is the Marianas Trench. Guam's right around where this hand is. But if we zoom in, you can see how deep it is. Okay, there's a lot of difference in relief. Okay, so this is a very, very deep trench. They're visible if you're looking at a topographical map. You have the same things over here, but this is the deepest one that occurs in the world. So let's get back to the PowerPoint. All right, the last type of convergent boundary is a continental to continental. This one is different because the continental crust, if you notice, the ancient oceanic crust does dip down below the lithosphere, but it's not bubbling up and it's not creating volcanoes. It would have in the past, but now that we have this continental crust here, the continental crust is kind of shoving together and it smushes together and it creates very, very high mountains. I wanted to show you this other picture because I didn't want to give you the idea that one of them subducts below the other one. Continental crust will not subduct. Okay, so this image I don't particularly like. This one I like a little bit more. It just kind of smushes together and it makes these very, very high mountains. An example of those mountains would be the Himalayas. Okay, so you do not get any volcanoes with continental to continental convergence. Okay. The Indian plate used to be detached, as we learned earlier, and it shoved up into the Eurasian plate. And when they push together, they create these very high mountains. They are still pushing into one another. The Himalayas have evidence of volcanic activity because Indian plate used to have some oceanic crust. When that oceanic crust was pushing into the Eurasian plate, it was being subducted, melting, creating all these bubbles and volcanoes. Okay, but now that it's just continental to continental pushing against each other, they just smush and they're getting higher and higher and higher. Okay, again, picture right here. Some of the oceanic crust would have gone into there. Okay. Oh, it's so beautiful. Quick fun fact. Mount Everest, because there's no way to really clean the stuff off of it, and because there's so many people trying to climb it now, has a huge problem with getting rid of human waste and all sorts of human garbage. So if you ever go there, you might want to reconsider and make sure that you've, made sure that you have taken into account that you're going to see a lot of human junk and crap. Cool. All right, last one, transform boundaries. Basically with these, we have the sliding against each other, okay? All along the western United States, we have this very famous fault called the San Andreas Fault, and these two plates are just kind of sliding against each other very slowly. We have known for a long time that they're sliding against each other, and we predicted that there should be a very, very large earthquake that occurs out there at some point in the future. People are just kind of waiting for it to happen. So this is a picture of the San Andreas Fault. It's about 1,300 kilometers long. And it's moving at a rate of 5 centimeters per year, just to give you some perspective on how fast some of these things are moving. But all right, so here's what I wanted you to know from this video. You need to be able to identify the plate boundaries. We're going to have to do that. You're going to have to tell how the different types of crust interact with one another. Identify what features are created by the different boundaries, and you need to explain how those geologic features are made. All right, so once you have reviewed this and you're ready to go, there's going to be an assessment on lightning grader. I want you guys to take that real fast. Quick thing just to help you guys out to, give you a little bit of a memory hook, I guess. We made up it's not a dance. I know I wouldn't take this to teen night. Somebody's gonna make fun of you guys, but there's a little hand motions or whatever you want to remember what the different types of plate boundaries are. Okay, so this is convergent, divergent, transform boundaries. Okay, now, I had students who got all into that and they had a dance contest last year. I wouldn't recommend that again. Don't do that at teen night. People will make fun of you. Convergent, divergent, transform boundaries. Okay, so hope you guys enjoy your time watching this video, and good luck on your assessment. We'll see you later.